Hello and welcome to our module on isomers. Today we'll be going over what a structural isomer is firstly, and then we'll be going over what a stereoisomer is. I've also included two sections. You might want to look over them, but they're outside the scope of the syllabus, and that includes a section on chirality. So the first thing we need to distinguish is a structural isomer. A structural isomer is two compounds, or two or more compounds that have the same molecular formula. So when you write their formula down, they're the exact same, but they have a different structure and name. And there are three distinct types of structural isomers that we need to go over: a chain isomer, a functional isomer, and a positional isomer. So the first type of isomer that we're going to go over is what's known as a chain isomer. So on the left-hand side, we have a linear molecule. This is butane. So meth, eth, pro, bu, all single bonds, so that's butane. On the right-hand side, we have two methyl propane. So meth, eth, pro, so this is the main carbon chain, and there's a methyl group on the second carbon. So that's two methyl propane. If you count the number of carbons and the hydrogens, you'll see that they both have a structural or molecular formula of C4H10. However, they obviously look distinctly different when we draw out their structures, and they also have different names. Thus, this is an example of a structural isomer, and in specific, a chain type of structural isomer. So the next type of isomer that we need to go over is a positional isomer. So in your head, you can think of structural isomer as the overarching theme, and then underneath it, you can have a chain, positional, and functional type of structural isomer. And recall that a structural isomer is two molecules with the same structural formula, but different names and structures when you draw them out. So back to our positional isomer. So recall from our video on naming that the functional group, in this case bromine, can take different positions on the carbon. So in this case, it's in the first carbon. In this case, it's in the second carbon. Again, both of these compounds will have the same formula. However, there's a big difference when we write out their names and also when we draw out their structures, as clearly highlighted. So in the third type of structural isomer, we have what's known as a functional isomer. So instead of there being a chain, as there was in a chain isomer, or the functional group being in a different position as in a positional isomer, in a functional isomer, we actually have totally different functional groups altogether. So on the left-hand side, you should recognize that that's an aldehyde due to the aldehyde functional group. On the right-hand side, this is a ketone due to the ketone functional group. If you count up the oxygens, hydrogens, and carbons, they'll give you the exact same structural formula for both compounds. However, one is propanal and one is propanone. So two very distinct compounds with different names and different structures. So as with all things in chemistry, you should always ask yourself, why is this important and why am I learning it? So isomers, whilst they may have the same molecular formula, are very, very different compounds. So not only do they have a different structure, a different name, they also have different physical characteristics. So what do I mean when I say physical characteristics? That includes the melting and boiling point as well as their density. And I've got a small example here. So on the left-hand side, we have a linear compound, pentane, and on the right-hand side, we have a chain isomer. So we have two dimethyl propane. On the left-hand side, it's a little rudimentary, but you can clearly see that I can pack in pentane a lot more closely. So this length here is a lot more close compared to this length here between these carbons, right? Thus, the intermolecular bonding, we'll have a separate video on intermolecular bonding, so refer to that if you are not familiar with that so far. But for now, the intermolecular bonding between these pentane molecules is going to be a lot stronger than these molecules due to the shortened distance. Thus, the linear versions of the isomers will tend to have higher melting, boiling points and higher density. Again, these differences between structural isomers isn't just extended to branched versus linear. We also learned two other types of positional structural isomers and functional structural isomers. These differences in physical characteristics are actually more apparent in the positional and functional type of structural isomers. And to show you this, I've actually got two molecules here. On the left-hand side, I have trimethylamine, and on the right-hand side, I have propylamine. So, if you're not familiar with hydrogen bonding, please refer to our video on inter and intramolecular forces. But if you are familiar, just recognize that propylamine actually has two NH bonds. So it's actually got two of these bonds, right? Whereas trimethylamine doesn't have a single NH bond, does not have any of these. Thus, propylamine will be able to make a lot more and a lot stronger type of intermolecular bonds, as it can make hydrogen bonds, compared to trimethylamine, which can't. Thus, this will have a higher melting, boiling point, as well as density. You can also see that you can use some logic in regards to how a molecule is shaped and what type of inter and intramolecular bonds it'll make to give you a indicator of its melting, boiling point, and density. And those are some questions that you're going to get. So you'll be given two molecules, you'll be told to analyze the functional groups and then look for differences in melting and boiling point and density and explain why that's the case. And hopefully this little demonstration has shown you how to do that. So another type of isomer that we need to go over is a stereoisomer. So stereoisomers are isomers that, again, have the same molecular formula. So if you see the word isomer anywhere, just know that it means or is congruent to having the same molecular formula. Stereoisomers are actually a bit different from structural isomers. So in structural isomers, we have the same molecular formula, but the whole structure of the molecule is different. In a stereoisomer, the structure is very much the same, but how the atoms are arranged in space, so in 3D space, are a bit different. And I'll show you some examples in later slides. I'm going to put a little asterisk next to this point. This is outside of the scope of Year 12 chemistry, but it becomes more relevant if you choose to do chemistry or chemistry subjects in university. So the second point refers to chirality, and there's a section at the end of the video. However, in regards to Year 12 studies, this, in regards to stereoisomers, will mainly apply to cis and trans structures in double bonds. So that's something you really need to know well. So these two compounds actually highlight the differences in stereoisomers present with double bonds. So they have the same molecular formula, C4H8. They have the same name. So that's actually something that's a key difference between stereoisomers and structural isomers. Structural isomers will have the same molecular formula, but different names. Stereoisomers will have the same molecular formula and pretty much the same name, but they'll differ in the way the atoms are arranged in space, and that's what I'll show you now. So these are both 2-butene. So it's a butene with the double bond in the second space. So if we look on the left-hand side, and I isolate this double bond, we've got one methyl branch on one side of the double bond, one methyl branch on the other side. On the right-hand side, we have methyl branches on the same side of the double bond. So that's kind of what I mean when I say stereoisomers are isomers that differ in the way that atoms are arranged in space. So clearly you can see that if the methyl groups are on either side versus one side of the double bonds, that's a difference in the way the atoms are arranged in space, right? Also, I should just tell you, it doesn't matter if it was like this. So if the methyl groups are arranged on the other side, it would still be the same compound, right? Because we can rotate it. So this is just a 2D representation of the 3D structure. So we need a naming system that differentiates between compounds on the left side and compounds on the right side. So this is what we call a trans structure, and this is what we call a cis structure. A nice memory aid that I use is trans always means across. So transatlantic, like a transatlantic ship, means across the Atlantic. A trans stereoisomer means that it has carbon chains on either side or across the double bond. A cis will have on the same side, right? So to answer the question of why this is important, this being stereoisomerism, we actually need to look at the polarity, or rather the change in polarity between cis and trans molecules. So on the top, we have an example of a cis molecule. On the bottom, we have an example of a trans molecule. Due to the distribution of electrons, this carbon here will have a slight negative charge, and this carbon here would have a slight positive charge, indicated by the delta negative and the delta positive. And this kind of makes sense because that double bond houses a total of 4 electrons, so that's a really electron-dense area. Electrons are negatively charged, so that carbon will have a delta negative charge. Thus, the carbon that's attached to it will have a slightly positive charge, right? Okay, so there's a net force in this direction, right? And then that's the medium. So if you look at the trans molecule, there's a net force in this direction attributed by this polar molecule, and a net force downwards attributed by that polar molecule, as there is a charge on either side, a positive charge on either side of the double bond. So there's actually no net force. So overall, whilst it may have polar contributors, this molecule is non-polar, whereas this is ever so slightly polar. This creates stronger intermolecular bonding, so thus cis molecules will have a higher boiling point. So, also one thing I want you to notice, boiling point refers to mainly, in regards to your scope, is how strong the intermolecular forces are between the molecules. Melting point is how closely they can pack together, right? You might refer back to earlier on, I gave you the differences between pentane and 2,2-dimethylpropane. Pentane could both make stronger forces, intermolecular forces, and could closely pack together. So thus it has a higher melting and boiling point. The cis molecule has stronger intermolecular forces due to its polar nature. So thus it will have a higher boiling point. The melting point is where things get a bit interesting. So this cis molecule can't pack as neatly close together with other cis molecules as this trans molecule can. And this is actually apparent when you have longer chains. So this trans molecule will tend to be a lot more linear. And if things are linear, we can pack them nicely. Thus, the trans structure will have a higher melting point. Those are the two key high yield associations. Cis molecules, higher boiling point due to the polar nature. Trans structures will have a higher melting point due to the linear nature and in which they can be packed together. So although this is another reason why stereoisomerism is important, this is outside the scope of the syllabus, so you don't need to pay attention. However, this is good not only for your general understanding, but also might help you in uni. So cis and trans isomers are actually really important when it comes to drug design and drug discovery. So the receptors in your body will tend to favor a cis or trans structure more or less, right? And this is best shown by the drug cisplatin, which is an anti-cancer drug. The trans isomer, which we call transplatin, has absolutely no efficacy, it has no anti-cancer properties, but the cisplatin does. So that shows that when we're discovering drugs, we need to kind of filter out that cis or trans for whichever one works best with the body / receptor / what it's trying to actually do in the body. So whilst this section on chirality may be outside of the scope of the current syllabus, it's definitely important to understand in chemistry and university. So if you'd like to listen to this section, feel free to. So the most important thing you need to understand is a chiral carbon is a central carbon with 4 different functional groups attached to it. That's the stock standard definition. There are some other buzzword definitions such as non-superimposable mirror images. However, I think getting an understanding of chirality is much better than just memorizing these concepts. So what I'd like to do, or what I find is easiest to visualize the concept of chirality, is using my hands. So if you look at your left hand and your right hand is pretty much a perfect mirror image of your right hand, right? It has pretty much most of the same components, hopefully all the same length, and they're perfect mirror images. Now, apart from flipping your hand over and trying to put it on top of your other hand, if you just try to rotate your hand palm side up, there's no way that you can make your left hand, for example, impose or superimpose on top of your right hand, right? To give it the exact same shape. So this leads us to the concept that if the mirror image of something is non-superimposable, they're two different compounds, right? And those are what we call enantiomers. Now, I don't want to get into it too much, but that's the crux of it. So if you look at this molecule on the right-hand side, right? This is a perfect mirror image of this molecule on this side, right? No matter how we try and rotate this around, we can't impose it on top of this. So if we try and rotate it about a 180-degree axis, there is no way that we can make the compound on the left. And that's pretty much what it's saying. Also, this thing means it's coming towards you. This means it's going away from you. And this means it's in the same plane, right? Just bear that in mind. If you look at the second example, it's got two of the same group. So two chlorine groups and one fluorine and one hydrogen. So it's got two chlorine groups that are the same. In the first example, all four are different. Now, if we look at the mirror image, right? So fluorine flips to the other side, chlorines come over. If we rotate, clear the ink. If we rotate this about this axis and the chlorines swing over to this side, we'll get this structure here. So thus, a chiral carbon, being a carbon with 4 different groups attached to it, its mirror images are non-superimposable. So the mirror images are 2 different compounds. That's pretty much all you need to know.